Today on The Future of Everything, the future of transportation energy systems. So in the past couple of years, we have seen an astounding move in the automotive industry. Electric cars have gone from a novelty created by just a few companies to a critical part of the strategic plan for almost every automobile manufacturer. We've heard announcements from Volkswagen, GM, Ford, Toyota, and many, many others that have publicly declared huge investments in the creation of electric vehicles and presumably the infrastructure to support them. And this is not for the distant future. This is something that they're planning on doing very soon. It's quite startling. The Ford F-150, which is the most popular selling car in the United States, is coming out as the electric Ford F-150, the Lightning, in 2022. This show has no connection to Ford, I should mention. So as we think about this rapidly approaching future, many of us focus on a few issues that kind of seem obvious. What is the range of the electrical vehicle between charges? How well will the batteries hold their charges as time goes on? Where and how will we charge the batteries when we're not at home? I sure see lots of gas stations, but I don't see yet as many charging stations. And how long will these batteries last? And do we have a plan for what we're going to do with them when they're no longer usable in terms of the environment and just getting rid of them? These questions all go directly to the issue of how good are the batteries we are using, how good is our energy infrastructure for supporting the recharging of these vehicles and others. Because there's other parts of our transportation system, trucks, trains, even electric planes I saw in the news the other day. These issues are not just about economics, but about sustainability and the environment as we, of course, try to mitigate climate change and ensure a safe and clean energy. Professor Simona Onori is a professor of energy resources engineering and electrical engineering at Stanford University. She works on sustainable transportation and automotive energy systems with a focus on both battery technology as well as optimization of gas-powered or combustion engines, and the use of battery technology not just for individual devices, but as part of the grid, the electrical grid. Simona, is the industry prepared to create and use the batteries that will be required very soon by, for example, all of these car makers?
Hi, Ras.
Hi.
It's a real pleasure to talk to you this morning. That's a very important question you're asking. Are we ready? Are they ready? And I'm going to use we because it's our problem. We work with the industry. Our group works with automotive industry sponsor here in the Bay Area and also in the Michigan area. I would say that we are very close to be ready. Yes, we are understanding so much about lithium-ion batteries and what it concerns to the electrochemical reactions and how those affect the system-level performance. And what we're doing in my group, for example, is to take all this understanding and put it in algorithms that we can then flash on the battery management system that works on electric vehicles, for example. And one of the main challenges is to understand how long those batteries are going to last. And on top of that, also, how many miles you can still drive with your fully charged, event. Those are very, very important information that the driver wants to have when they drive their vehicles. And so I believe that we are ready. There are still challenges that needs to be tackled, but we are on the right track.
So maybe let's go back to basics for people who don't think about batteries all the time. You've mentioned lithium batteries. I think that's the reigning, until something changes, we're talking about lithium. Can you give us a little thumbnail sketch of how a lithium battery works? Is lithium rare or is it abundant? And maybe just a little bit of background so that when we get into the rest of our conversation, we'll have the basics.
Of course. So lithium-ion battery is an electrochemical energy device. So it stores energy by means of electrochemical reactions in the forms of oxidation reduction reactions. And the battery is made of two electrodes, anode and cathode, and a separator and electrolytes. And the electrolytes, you can think of the electrolytes as a filter that allows ions to shuffle back and forth between the two electrodes. and it prevents electrons to basically go from one electrode to the others. So electrons are forced to go outside the circuit and to basically be sent to a load. And that's what happens during discharging of the batteries when the lithium is all basically in the anode. When we charge the battery, what we have to do is to provide some external work or potential. So we need to basically apply a voltage to the battery that forces the electrons to go to the anode, and the ions basically now they go from the cathode to the anode and they recombine with the electrons.
And cathode is plus and anode is minus for those of us who've looked at our batteries.
That's correct, yes. And we have this separator again that prevents electrons to pass through, and they only allow ions like electrolytes. And so lithium-ion battery is a family of battery. There are different flavors of this type of technology. The ones we use today on electric vehicles, or also in consumer electronics, a laptop, or also in your electric vacuum, they use graphite at the anode, and they use different types of metal oxides at the cathode.
Okay.
And the metal oxide is this combination of different metals. For example, the most common one that you might find in the electric vehicles is the one that uses nickel, manganese, and cobalt. In hybrid vehicles, on the other hand, or in power tools type of devices, we use LFP, so iron phosphate. In consumer electronic, we use lithium cobalt oxide. So there are different type of flavors which are selected depending on the specific applications that are being used.
Great. And do we have enough lithium? Is lithium a relatively abundant element?
It seems like so. And actually, there's been a very recent study by some of my colleagues here at Stanford. They said that you can extract lithium also from seawater. So lithium won't be a problem. It's not a problem. It's there and can be extracted. Cobalt is a metal that is added in some of these lithium-ion batteries that provides higher energy density. That can be a resource that we need to be very careful about. There might not be plenty of it, and also the place where we extract cobalt are very limited. So there are just a few areas in Africa, in the Democratic Republic of Congo, where we can extract that, and over there they use child labor. So there are efforts done to develop cobalt-free batteries, for example, on one hand. On the other hand, they're trying to look at to use, for example, for electric vehicles, batteries that do not use cobalt at all, like iron phosphate, at the price of limiting the range. Because iron phosphate batteries have lower energy density than NMC or batteries, for example.
Okay, good. So, okay, that's very helpful just to set the stage. And I actually know that I want to ask you about your work, which is these, as you mentioned briefly, the computational and instrumentations to actually monitor how the batteries are doing. But before we get to that, let's go all the way to the end. What do we do with old batteries? Do lithium batteries die, or do they fade away? And do we have a problem at the other end of the pipeline? Because I'm sure people wonder about that.
Absolutely. Do we have a problem? Yes, there is a concern about what we're going to do. So we have an uptake of EV, right? So we're going to find and see more and more EVs on the roads worldwide. And we know for a fact that those lithium-ion batteries, age, and then they will die. When they die, what it means is that they don't provide the energy and the capacity that it's needed to really, for a trip.
Yes.
And so you cannot rely. So they're not reliable anymore. That doesn't mean that those batteries are completely dead. It means that the capacity, so we consider a battery dead for automotive purposes when its capacity is below 80% of its nominal value. So
oh wow, that's pretty strict.
It's very strict. because drivers are very demanding.
Yes.
So it's very strict. So what that means, on the other hand, is that there's still so much energy and charge you can have in those batteries. And the question is, what do we do with those? And so we are seeing now startup companies that are focusing on recycling. And so trying to extract all those metals out of those batteries, which is a great news. They can extract up to 95% of those metals, so nickel, manganese, and cobalt, which can then be reused to make new batteries.
Right.
And so that's a great news. So there is another component to the problem, which is what do we do between the time a battery retires from EV application, so electric vehicle application, to the time where the battery is being recycled.
Yes.
So can we give those batteries a second chance in their life and use them for a second life application?
It's like an old professor who needs to do a radio show or something in order to be useful.
Yeah, you can say so.
You don't have to comment on that. Okay, so between 80% and dead, there might be some opportunity.
There might be some opportunities. So how do we assess those opportunities? Does it make sense for those batteries to be used, for example, in grid storage application? And if so, how long are going to last? So those are the questions we're asking ourselves these days in our lab. And there is another component to the problem, which is a battery pack is made of hundreds or thousands of cells. And so you might be in the situation where a few cells are damaged, wrongly damaged, which we cannot use anymore, and actually a very it's very dangerous to keep them there in the battery because they can affect other cells. Right. And trigger thermal runaway, and and the battery can catch on fire.
We've heard the stories about the exploding lithium batteries, and it's not pretend. This is a real phenomenon.
It's a real phenomenon. Then those batteries can reignite, right? So they catch a fire. You're trying to put off the fire, but then they can reignite as well. So it's unsolved problems these days, and so they need to be managed with care. And that's what the battery management system does, basically. And that's what we develop, battery management system. So going back to your question about Second Life battery application, we're trying to understand, first of all, there are two dimensions here. Batteries that retire today, how we can assess their value, their life, and whether or not they can be used for a second type of application. And the other question we are asking ourselves, what can we do at the very beginning of developing the BMS for EV that will allow us to then reuse those batteries right away? Okay, so today the way we estimate remaining useful life of the batteries in EV is not accurate. So that's automotive industry does this type of estimation and predictions in a very, I would say, approximate way. They don't use sophisticated tools like electrochemical models or observers that are based on control theory to make an accurate assessment of the battery life. So it's very difficult to say how much life is left in the battery when basically the 8-year time of period of a car basically expires.
Right. No, and this, I'm sure this resonates with everybody because we've all had a battery indicator of some kind, which seems almost unrelated, not quite, but almost. But so I know this is the area that your group has specifically focused on. So tell us, what are the kinds of things that you are doing to better assess the current state of a battery and the rate at which it's aging and whether it needs to be taken out? Especially, I like what you said about how these are not monolithic batteries, they have components, and it strikes me that maybe you can identify some bad eggs, take out the bad eggs, and then make the overall life of the battery pack go longer. So what are some of the principles that you use when you're trying to understand in more detail these measurements that you were mentioning?
Right, so we're trying to use the knowledge of electrochemistry. And in particular, we're trying to understand how the intercalation processes work and how those affect aging in terms of, for example, a solid electrolyte interface, which is the major aging mechanism that you will find in a lithium-ion battery. And so we understand.
This is where the lithium comes in contact with basically a solution of chemicals, and that interface erodes or evolves over time.
Correct. So basically, it's when the electrolytes get in contact with the electrode, the negative electrode, in this case, the graphite, which is very reactive. And then the product of these reactions results in a passivating film that forms around the electrode particles. And this film keeps growing over the years. And what it does is effectively eats up lithium, which is not available for reactions anymore. And so that's why capacity fades. There is less and less lithium that can participate to the reactions and give rise to electricity effectively. And so we try to understand mathematically how this passivating film evolves, creates, and dynamically change over time. And then this understanding is brought into a framework that we call a control framework, where we look at what each electrode does and try to reproduce that through some algorithms. And the second move that we add to this, so the second part is to relate this increase of solid electrolyte interface film to capacity fade and resistance increase.
Yes.
So it's not just about capacity, so less availability of charge in the battery, but also the fact that impedance increases, so resistance increases. That's a very important metrics of aging because that affects the power. So how good you can accelerate your vehicle, which is an important feature that you want.
Another thing that the driving community is very sensitive to.
Yes.
So will you? So is the vision? I don't actually know. Are these batteries sealed and you never open them, or do we foresee a future where maybe you have instruments making measurements of the internals of the battery to inform your calculations? I'm making this up. I'm just asking. Are we going to start biopsying? That's what we would call it in medicine. Biopsying the battery to see how it looks, or can you infer that all from its electrical behavior and you don't need to check?
Right. So, yeah, absolutely. So we make current and voltage measurements out of each cell in the battery, and cells are put together, connected together in series and parallel to create a module. And then usually a battery pack is made of few modules together.
Okay.
And so there is this hierarchy that is implemented in a battery pack. So physical measurements consist in voltage and current. But there is in temperature, you have distributed temperature sensors across the pack.
Yes.
There is just so much you can get from current and voltage measurements though. So using electrochemical models, what we do, we create what we call it virtual sensors. So ways to understand the internal dynamics of the cells and the modules and the pack. Okay. Going back to your question, what is the stage at which we want to diagnose the health of each cell? We diagnose the health of each cells. That's very important. If you find that, and it's very important because an aged cell might affect the health of a module the cell is interconnected to, which then in turn can affect the health of the pack. So it's very important to go to the type of granularity. And so we run these electrochemical models and observer on each cell. And now, what stage you want to disconnect the cells or remove the cell, that is really a question to the automakers. What is that makes sense from an economic standpoint? So that's still, to me, still an open question. So today, what happens if you're driving an electric vehicle and you see a signal, a light on the dashboard that says, go to the dealer, go to the mechanics, what they'll do, they'll run some diagnostics, basic diagnostics. And if they find out that there is a module in the pack that is more degraded or doesn't perform like the others, we'll replace the whole module, the whole big piece.
Yeah.
And they'll put a new one in it. What that creates, on the other hand, is heterogeneity in the pack, because now you have other modules which have been used for example, for a couple of years, and you put a new module with new cells, and that creates an imbalance in terms of health that is not addressed today, for example. And so that's another research that we're looking at in my lab.
This is The Future of Everything. I'm Russ Altman, and we'll have more with Professor Simona Onori next on Sirius XM. Welcome back to The Future of Everything. I'm Russ Altman. I'm speaking with Professor Simona Onori about batteries, electric vehicles, and grid storage. And so one of the things you were talking about at the end of the last segment was the work of your lab in creating the capability for very high resolution measurement of the performance of a battery, how it's doing, how it's aging. You mentioned these films that form and how they degrade and create problems with resistance and whatnot. And this is leading to the creation of hardware to make these measurements. And I'm wondering, how is this still a laboratory oddity, or are we starting to get to the point where you can imagine hardware, that can be built at scale for the industry?
Yeah, so that's the very first question we ask ourselves when we build those algorithms. And so because we combine electrochemistry with control theory, and that we provide a few lines of code there in our algorithms, the question is, are we doing this for ourselves, or is this algorithm something that can run in a real hardware? Because that's what ultimately we want to do, right? We really want to make those battery perform better. So there are material scientists who look at creating new materials for electrodes and create better batteries. We want, on the other hand, once we have those batteries, find ways for them to last longer and perform better. And so in our lab, we tested and created hardware that verified our algorithms effectively functions the same way as they function in a computer. And so that is a very, very good news for us, very promising. This is a very promising technology, which we hope to see implemented in the vehicles in the very near future, and it's going to happen. The industry really understand the need to go more sophisticated in terms of battery management system algorithms.
So, and just so I understand, is the vision that there will be a new component under the hood of a car that is this hardware that contains these algorithms and these monitoring systems?
It's the hardware will be combined with the software, so the algorithms, and they will be under the hood, exactly. So on top of the battery pack, you will have this kind of big brother running, monitoring all those cells. And those cells, I brought one here today. It's a cylindrical cell. And you might usually have thousands of those in a battery pack in electric vehicles. So
this looks like about 3 inches?
So this is called 2170, and it's a cylindrical cell, and it has 21 millimeter diameter and 70 millimeters length.
Okay, and it looks like it's bright red. And are those actually in production use currently?
Yeah, absolutely, yes.
And
so these type of batteries are used in the Model 3, for example.
By Tesla, yes. Okay, so that's interesting. This idea that you're going to have this, I like the idea of a big brother hardware watching. So that's going to create pressure on you and your lab or somebody, because there's going to be pressure for downsizing that, making sure that it is compatible with the form factor of the cars. So right now, if you have a battery of a certain volume, what is going to be the volume allocated towards the control and oversight of that battery?
Not much. Not much, I would say. It will be just the efforts is to make this solution, this technology, as integrable as possible with existing hardware. So we don't really want to add more. Adding more is never a good thing. So we want to be working with the existing hardware and make it better, make it work better through the software mostly.
Now, what you showed, well, you described the cylinder, and they just look like long batteries. They're just cylinder batteries. But my question is, do we imagine that we're going to instrument you said there are thousands of those in a typical EV, electric vehicle. Are we going to be able to monitor every single cell inside the battery pack? I think from what you've said, that would be revolutionary, because that is not what is currently done. So, this technology is compatible with monitoring thousands of cells at the same time, and then perhaps having extremely precise prescriptions about what's wrong with the battery.
So in today's car, each of these cells comes with a current sensor and a voltage sensor. What we will add basically is this new feature that allows to monitor virtually, I would say, internal states of the battery, electrochemical states and the SCR layer. And that can be done, it will be done for each single cell. So yes, that's
got you. And you also use the term control theory, which I know a little bit about, but I'm wondering is if you imagine that in the vehicle, based on the data that you're collecting with this hardware, you might make decisions about what in computation we call it load balancing, where you say, I'm going to change the demands on this cell. I mean, are we imagining a world where it's dynamically reconfigurable, or is that a fantasy right now?
No, it's not a fantasy at all. What you're talking about is actually what it's called active balancing.
Okay.
In active balancing world or framework, each cell comes with a DC-DC converter, and the idea is to control each of these cells in a way that all the cells are being charged or discharged at the same rate, so that you don't have any imbalance within the pack. Imbalances are always bad,
right?
Because they create conflicts among the cells, which you have to resolve.
Yes.
And active balance is a very efficient way to do it. It's not done today, on the other hand, on vehicles because it's an expensive solution. But for some application where cost is not an issue, we will see more and more active balancing technology being applied.
Yeah, I find that exciting because it's not hard for me to imagine that the different cells may be, for whatever reason, they may have different loads over time. And so if you want to get a really good acceleration, you might be able to configure, I don't know, I'm just making this all up, but the idea of actively controlling sounds exciting. So as we have about 2 minutes left. What is the outlook for consumers? Are they going to notice changes in these parameters over the next 5 years, or is this more of a 20-year horizon for when they'll start to see the fruits of these kinds of technologies in their cars in terms of the battery life, the acceleration, and the charging times?
I think the outlook is very positive, I would say. So we're seeing at the declining cost of the battery cells. So they're cheaper and cheaper as we speak. On top of that, we are very good at using them more efficiently today through this algorithm. For example, one of the key, for example, in some cases, to use cloud computing, where we can run very high computational, lengths of codes, and then send to the vehicles the information that it needs to know.
And that's for individual vehicles.
Yeah.
Oh, that's fun.
So, that's fun. So we are seeing that there are so many efforts done all around the battery pack, all around the vehicles to make it cheaper, to make it last longer, and performing better. And I also want to add this is not just those improvements are not just being implemented in electric vehicles, but also on the power tools. I don't know if you have an electric drill or a vacuum, which
yes, my grandson calls it my magic screwdriver.
And I call it my magic vacuum because I love it. And, if you buy one today, it's much better than the one you bought 2 years ago. And yes. It's just within the span of 2 years, you see much more improvement, which is, you can have much more fun cleaning your house, for example. Small things. And, your laptop, the battery on your laptop lasts much longer now. So you don't have to keep charging, be anxious about finding an outlet to plug your laptop. So definitely the future is bright in this sense.
And the importance of lithium batteries to all of us will rapidly be increasing. Well, thank you very much. And thank you to all for listening to The Future of Everything. I'm Russ Altman. If you missed any of this episode, listen anytime on demand with the SiriusXM app.